Greetings, gentle, generously reading readers and courageous fellow earthlings. Today in Reading Foundations with Ross, A. Finlayson, myself. It's going to be more of reading this box of books. The next box of books is a lot of quantum mechanics. Important works and varied works from the theory of quantum mechanics. Quantum mechanics together with general relativity, or the theory of relativity, are said to comprise the most of fundamental physics. These are premier theories of the day, our first premier theories. Relativity theory is simple in a sense, because all that relativity theory says is there's no absolute motion. So it's really only relativity of motion theory. And Einstein, in his book Out of His Later Years, raises the point, is like, well, how can such a simple negative stipulation, because otherwise it would be absolute, of relative motion make for a theory that holds good and is successful at all? Well, the idea is it basically makes for matters of perspective and projection that those are free. And then the coordinate settings about setting up for general relativity, whose goal is to equal in the limits the classical theories of Newton and so on. And as with regards then to mass energy equivalency and the cosmological constant, Einstein's great blunder, as sometimes he put it, but now matter-of-factly, kind of for the Duhamel principle, the least action, least gradient accommodation, the cosmological constant in the gravitational field equations, making for why relativity of the theory is Newtonian in the limit. And the relativity theory is then also usually given in its formalism, it's being about the Laplacians, the sum of second partials is something in its various dimensions like x, y, z, the sum of the second partials, which has lost the corners in the around bit. So the second order partials, their sum, the Laplacian, then has plus minus, according to a sign convention, the second order partial of time terms, equaling that to, instead of 0, as would be for the theory of harmonic functions as it's usually given, that being called then the theory of potentials, when really it's just the theory of harmonic functions in the limit, or where the Laplacian equals 0. Then instead, this Laplacian plus minus this other Laplacian in the space and time equals the metric, the second order partial of the metric, and then also sometimes whether that's ds squared, because it's written is with the raw differential, and so according to the formalisms of mathematics, that's kind of let out. And Tullio Levi-Civita gives a brief account of this in what he calls the indefiniteness of ds squared, or the metric, as with regards to why then the Laplacian, the Lorentzian on the other side makes this is altogether the Lorentzian. This is the Lorentzian. And so the Lorentzian invariant, as it's put, has that anything that satisfies just observing these partial accounts, truncations, reductions, the merely partial half accounts, having the accounts, is a model of relativity theory. So when Einstein says, hey, how can this be a theory that holds good and is successful at all? It holds good in the first order approximation for things like the mass energy equivalency and the cosmological constant, or Einstein's great contributions. Otherwise, this theory that was written down already and used in various accounts of the reductionism to reduce it to this. Then not that it's complete, but that it's fungible, to be sensible, fungible, and tractable. That then relativity theory is for the account of restricted relativity, usually called special relativity, originally called restricted relativity. Another account of reductionism. Then there's light speed as constant. And then so for accounts of mass energy equivalency and light speed as constant, that gets in the whole universal speed limit of light and all this kind of stuff in the usual account. So relativity theory that's it. And the rest of it is kind of just the trappings of the analytical setting. Hilbert space and complex numbers, Minkowskian, and for geometry, the Lobachevskian and the Riemannian and all this kind of stuff. Those are just loose pieces sitting around that somehow, any way they do, add up to make a Newtonian and Galilean account. So after the Lorentzian, then there's first like Galilean. So it's just an extension of the Galilean, and then just kind of having truncated that. Where the Galilean is just usually the idea of that velocity times time equals distance. That's all that really has. So a model of general relativity can, after its considerations of things like length contraction and time dilation, those making for the accounts of why there's like for Hafaele-Keating or Pound-Rebka, and then besides for Michelson-Morley, but mostly for Hafaele-Keating and Pound-Rebka, these being the names of experimenters whose experiments showed that relativity theory was confirmed, which is loose language for saying in science that it wasn't falsified. Has that. There are other ways to make an account of relativity theory, that there's any number of ways to set it up according to all these other fields in the forces, the fields of potential, the real fields here, and the forces, just the measurements or the, according to matters of perspective and projection, the relative terms of these things, vis-a-vis magnitudes and quantities, and the scalar, of course, the real analytic, the real analytical character thing for measurements and observables, for that our science is observable, repeatable, and falsifiable, the theory, the practice, the controlled experiment thereof. The relativity theory has at least one other way to make it from as more of a singular perspective, an original perspective, and a reduced perspective. So the idea today then is that there's double relativity theory. So it's relativity theory is just like there is no absolute motion. It's relative. Meters per second, it's relative. And then that just makes a coordinate setting where then these other things that got to balance out for whatever reason by whatever means do. So double relativity theory is just, well, then now there's no absolute space. And what's the point of this then, you might ask? Well, the idea is that when we talk about accounts of space contraction, instead of time dilation and length contraction apart, that's always space contraction, it's real space contraction. But then there's an account that there's a difference between the linear and rotational. For this, you can kind of consult the moment in motion series here, where it's arrived at the world's turn bit, the unlinear account. Is why the linear and the Galilean is different than the rotational setting. So for example, in the centripetal, when it's around and kicking in, or the centrifugal, where it's around and flying out, which one of those is fictitious towards each other, has that there's the balance of things. And here's the real centrifugal, the vis-a-vis the usual account given for angular momentum, that it's a real centripetal and fictitious centrifugal. So the accounts of space contraction linear and space contraction rotational are after this real space contraction, that in a theory of double relativity, that the, how one would put it, frame, which is relativity's account of no absolute motion, it's like a moving picture show. They're just instantaneous frames of things. So that's always the local absolute of each of these relative accounts. Frames and frames and frames and frames and frames and frames. Back from when the idea of a motion picture show was new to the world, frames. Then the idea is that there's frame spaces and space frames. So this is in accords with various accounts of ideas like, matter, and according to atomic theory, is mostly empty space. And so when matter goes forward in the linear, that it carries along with it some of the space as well. It's not just the massy body itself, it's also some of the space. So the massy body's in the frame, the inertial frame, it always is in relativity theory for general relativity. Its usual attachments to mechanics, and the space that is the absolute of that. And so a usual account of that would be saying, no, we always have to have absolute space. because then it gets into accounts of like space contraction, which is real, and so on. So then one can counter that to the relativists and say, oh, I'll be perfectly happy to accept there's an ether theory, and now you got all the reasoning that goes into why or why not there's ether theory, like Michelson-Morley and the other sorts of experiments. Since 100 years ago, for 100 years, these sorts of accounts. So saying that there's double relativity theory has that anybody who says there's not an ether theory automatically gets equipped a double relativity theory. Now, when I think this is plainly because automatically all the experiments that confirm relativity confirm it also in the loose language of the non-scientific sorts of empirical inductive reasoners. That thus leads to reduction. Is there further reduction? So the Lorentzian is just equipped with taking a third partial or squaring it. And automatically then, whether it's in terms of like power and resistance, power minus resistance or power divided by resistance, either taking the derivative or taking the square and reducing the terms once again and then making for so that automatically it lets out and then double relativity theory is natural in this sense. So that's what I thought I'd introduce today is like here there's an account of rest exchange momentum for the space contraction because it's like the hop, skip, and a jump. Or the idea of the compounding of the interest, or with regards to all the infinitely many higher orders of acceleration, as is also discussed in Moment in Motion and its consideration of mechanics. The kinetic, the linear, and the kinematic is the rotational. These two settings. So the kinetic and kinematic then is about the linear and rotational, make for these different and varied accounts. And then that's what would be considered for this rest exchange momentum, and then a light speed rest frame theory to go along instead of like, well, is light going always on the geodesy and at light speed that's pretty much infinite to everything else, and then the thing is moving not at all? Or is the frame essentially its light speed and light is just zero and left behind from that? So by having a rest exchange momentum theory to figure out Nessie's hump, these are the sorts of thought experiments that are a little bit more involved than Einstein on the train, watching a motion picture. And for example, Einstein in the Teacup from the reading from Einstein, out of my later years, has that, at least in part, then this would be influenced or inspired by reading Einstein, particularly his noted comment about, the success of such a simple theory of a negated stipulation of that motion is absolute, or that space is absolute. And then one's meters per second, the other's meters per meter, or seconds per second, in a sense. About still the same constants and quantities of motion and rest. That then the second thing to bring from Einstein's out of my later years is his attack on Newton. So what Einstein does is he carefully and deliberately says, I am here briefly to defend Newton's account. Because by then, for 30 years, people have been saying that Einstein toppled Newton. And that that's reserved and limited a little bit because relativity theory is just Newtonian in the limit. And it's only good at first order. And these sorts of accounts for still why things like real space contraction is real. And otherwise, the accounts of mechanics, according to Newton's system of the world, after Galileo's, after the Newtonian school, and all these accounts that went into it since antiquity, have it so that Newton's defense of Newton then is to say, and now I'd like you to transfer that projection to a defense of myself, Einstein, in my earlier years, because now I'm going to go about attacking myself indirectly by attacking Newton and the mechanics of material and bodies and matter as what must be some zeroth laws of physics before Newton's first, second, and third laws of physics, after Galileo's first, second, third laws of physics. Motion, motion, rest, rest, equal opposite collisions. There are no perfect inelastic collisions. It's always unlinear. Motion, motion, rest, rest. Is it always relative or absolute? Yeah, it is. And then for Newton's laws of universal gravitational acceleration, inverse square. And then force equals mass times acceleration has here that inverse square is just the classical impulse left in the middle of a real potentialistic account of a fall gravity, like Flavio Lesage. Again, hundreds and hundreds of years ago, and just left on the side, waiting to be picked back up again. And Newton's accounts after Galileo's, after Kepler's, basically having read Kepler's account of that the orbit sweeps equal area and makes an ellipse, and that's just perfectly like inverse square, and then making some calculus for that, putting together the pieces. Whether or not the apple fell from the tree and landed on Einstein's head, and he just imagined the whole theory of gravity. It was after he'd read Kepler, kind of Kepler's system of the world before Einstein's system of the world. That being after the system of the heavens or whatever it is from the Muslim Enlightenment, before that, because that's where algebra and analysis kind of came from. And then for Descartes, and whether Newton invented calculus, well, he kind of invented some differentiation, and whether Leibniz invented calculus is like, well, he kind of invented some integration, and that there are various deconstructive accounts of who actually invented the integral and differential calculus for real analysis. Is like, it's going to vary, There's settings in these practical. So the Einstein he's set up saying, and now I'm going to just say that later when you're having to confront that what was put up as Einstein's account of things is to get toppled, Einstein is like, stay clear. I'm going to go about toppling myself a little bit here. And then Einstein gets into, for his overall whole account showing it kind of consistent together with itself, he makes an account of mass energy equivalency that's rotational after the radial and centrally symmetric. As you can read from his books, after he separates the spatial and spatial for general relativity and special relativity as two different things, breaking it apart, breaking it open, deconstructing it, leaving them independent, free, and floating there. To then this account of that was like it's used in condensed matter physics, or after the paradoxes, as they're put sometimes, of Einstein, Podolsky, and Rosen for condensed matter physics. But it lives right in mechanics, and here that's just for the counts of spinning projectiles and Hef, as Sadov, the Soviet guy who headed the Soviet space program for 30 years, was responsible for all of its successes in the 20th century, always includes the gyroscopic terms in his systems of equations, and also a continuity equations or relations, the constituency of continuity. So it's a continuum mechanics. And then the idea of double relativity theory is making for the space frames and frame spaces to complement the idea of otherwise frames, which is everything in relativity theory, so that it's all and then stacked up according to whatever coordinate relations, the relation to the invariant of the Lorentzian. Then that's here that's for the account of all these different Lorentzians, the F-Lorentzians. Fizeau and Fresnel about light. They have different accounts, but both can make these Lorentzians their accounts. Fatio and Freundlich for gravity and gravity, because Freundlich was basically Einstein's second. And then Finlay-Freundlich, the same guy, because that's when he was still like, well, special relativity was first or second. So about light and these kinds of things together. So then for electricity and magnetism, there's Faraday and Fitzgerald. And then there's Feynman, in a sense, because that's touching down into the quantum side and then trying to bring it all back together. So really when F-Lorentzians is about forces and fields, and then equivalency is about energy, and Einstein's account, usually enough. After electron physics, then thusly, this is considered a kind of a mnemonic, yet as well kind of a setting of why then this double relativity theory is eventually kind of like infinite relativity theory. And it's absolute. and that also it's a potentialistic setting, and it's true and it's real. So for somebody who's interested in a theory of everything and foundations, it has a certain cachet to it that's unique in a sense. So then the next box of books here is about quantum mechanics, which is about continuum mechanics. Sometimes I'll be looking around and see somebody saying, hey, I'd like to offer to explain to you what is superstring theory. What is string theory? Okay, I'm interested in that. I've heard in the 80s and 90s that it was the next field of physics. It was the fundamental physics. So it's after atomic physics. And so then I'd be curious to know, it's like, well, what is this then? What are superstrings and superstring theory? Well, the account is that we already have atomic theory, and with that comes all the stuff to do with quantum mechanics, particle wave duality. After atoms, first of all, the idea of atoms is like it's infinitely small. It's an individuum of a continuum. And then to make that quantum is somehow having truncated or made partial, the merely partial, the half account, so that then we can talk about adding those up. And then, of course, this is after all kinds of accounts of, after Kelvin, who, as read here the other day, is like, infinity is what's real, not the finitude. He makes that perfectly statedly clear. And then there's the idea of the quantum is to get it to be fungible, sensible, fungible, and tractable, so it adds back up. So atoms are 25 orders of magnitude smaller than us by mass. And then 10 or 15, about 15 or more by length, and then about time. And then that gets into the quantities after Helmholtz constant, and then underneath that Planck relations. So then we have like the angstroms and Plancks, the angstroms being above the atom a little ways, a few orders of magnitude, and the Plancks being a few orders of magnitude smaller. So like electron microscopy and optical resolution ends there, according to the special character of light in these models. And then that mass and length and time kind of curl up in a little ball there in the middle of the atom, the atomic, uncuttable, is somehow a surface in a body of these things. And then for Avogadro's number, the great ratio, how many atoms per mole? How about 9.022 times 10 to the 23rd? It's derived from electron, whatever's the current measured value of the electron at rest in a vacuum, according to an imaginary virtual test particle. That's the stack that makes for constants, that then anything that changes at all involves then the extremes of the regimes, the Planckian regime and the angstroms, or where structural chemistry lives in these. Fritz London's, rather. Then has that the running constants are as after NIST CODATA, NIST particle data group's CODATA. They have all the tables of the constants that are current. System international units, it's like, well, this is how we're going to define a second and a meter and a gram or a kilogram. And that's just been reduced so that everything else is derived from it, basically according to a model of restricted special relativity. Because all the real units then are like, it's according to these constants by NIST PDG CODATA, CODATA, CODATA. And it's the running constants, and every few years they release new ones, and all the fundamental smallest quantities are smaller, more precise, and smaller. That this is real. And then the reductionism afforded by theories of relativity, or the quantum particle conceit, or here the system international derivation of units, is reductionism to the point where it's kind of run its course. Because then general relativity and quantum mechanics, while they made themselves so sensible, fungible, and tractable a piece, one in the kind of the global and one in the local, then they fail for each other 120 orders of magnitude in the middle. And there's no gravity yet, because that would be constantly doing work for free. It would violate conservation of energy forever, perpetually, the perpetuum mobile. So what are superstrings then? It's like, well, you know how hard it is to figure out what atoms are? And then we got particle wave duality, we got indeterminacy, or we got that it's infinitely fast, that there's the geometric mutation of units about mass, length, and time, and distance. In the atomic scale, the Planckian regime and the trans-Planckian regime. So anyways, that's 25 orders of magnitude down the atom. Superstrings are just twice that many. That's all there is really to it. It's just saying, okay, well, we got a quantum mechanics for a particle mechanics because it's supposed to be continuum mechanics, but now we're trying to relate everything to particles. And of course, there's all the great accounts of success of spectroscopy, the great success of the theory of electron orbitals, discrete again, and then quantum to be so fungible to add back up. So about the arithmetic, about the classical accounts of arithmetic, and then geometry on the outside of that. So that then the superstring theory has, well, it's just, if that's supposed to be continuum mechanics, here's what would happen if we tried to take continuum mechanics again, and then it's particles again, second particles. And it's just about a grainy substrate of, otherwise a continuous manifold of these things. And then trying to figure out for the dimensions, like, well, how do they roll up about, well, does superstring theory really have 26 dimensions? It's like, no, it doesn't really even have 4. It's got like 3.5. And then all these other dimensions are just added on for perspective and projection. A scratch pad, a bookkeeping, hopefully, and not just a waste book of extra numbers to then figure out from these outer products what can be left from the middle, the bright line of, as almost ubiquitously under the Cauchy-Schwarz inequality or triangle inequality, the metric and norm, those separately, but that must be the same according to all these various geometries and perspective and projection. That's what it is. And so can superstring theory ever make theory? It's like, well, yeah, as long as you kind of keep it real analytic, which is the challenge of it. And then it's like, well, does that mean there's a unique superstring theory? Well, if there's at least one. So from somebody like me who's always been, interested in knowing stuff, then and then having had a great high school education in chemistry and physics and all the linear curriculum, physics, calculus, chemistry, that I was equipped to get 5s on all the advanced placement tests, which I did, in English too. So this is the standard linear curriculum. And then later getting a mathematics degree, so for like the higher abstract algebra, the usual course that gives for modern mathematics. Then I studied modern mathematics and axiomatic set theory and descriptive set theory course, which I have studied and thoroughly deconstructed and put back together. As one can read from my 10,000s Usenet essays, or listen, hopefully, in an enjoyable manner from video essays like these. Then superstring theory has, here it counts for the Poincaré rough plane next to the Euclidean smooth plane. And then for geometry, besides the parallel postulate letting out the points meet in infinity, there's a double angle axiom of lines at the origin. And then those are infinitary and hyperbolic with regards to each other for these things like these Zeno swath and the hypercube distance. The geometry, instead of being super-Euclidean and then non-Euclidean, instead is like super-Euclidean and sub-Euclidean, super-Euclidean. All in theory, it's a continuum mechanics. Well, all right then. We left off here last time reading us from George Peppard's, or not George Peppard, that was a television actor. A.B. Peppard's Response and Stability, an Introduction to the Physical Theory. So generalized linear systems and stability criteria. So the stability and astability in dynamical systems is a lot related to convergence. And so convergence and emergence. So convergence is the idea of, usually introduced as part of real analysis, for sure, then in terms of systems of differential equations, which in the usual linear course are given as like the road to the mathematics necessarily present in their formalism for all such matters as of later tossing it at the computer and letting it crunch it. The sensibility, fungibility, and tractability. So convergence, and the criteria of convergence is for almost ubiquitously the infinitary expressions, whether that's infinite series or infinitesimals. And as the infinite series that converge necessarily have infinitesimal, eventually, terms. Or that they could have oscillating terms, where the usual definition of a limit would exclude the average of a sine wave from being zero, while you could just divide that by x, and it's always said to be zero. Vis-a-vis its range in the interval, and convergence, and criteria of convergence. So there are various definitions of convergence, and over regions, the bounds usually, and uniform and global convergence, and then fast and slow convergence. Some expressions don't appear to converge, they do. And then, for examples, where, for example, some convergence criteria would fail and others would pass. This is here often given as the account of Stirling, a mathematician's account of an approximation for the factorial function, a number times each number less than it, add in recursion ad infinitum, 10 times 9 times 8, the factorial function. He gave an expression that, kind of like Hadamard's expression for factorial, and I give another one, an expression for factorial in terms of other elementary terms. The square root of the sum of n to the n minus the sum of n to the n. Which is kind of a remarkable term, as with regards then to the factorial exponential identity, which is another expression in the infinitary, which provides some of this convergence criteria, which the standard account simply can't reach because it's always kind of growing from a place where it is from without ever getting all the way there, that the limit is the sum. So these matters of formalism have that after criteria of convergence is stability. And so stability kind of is at odds again with one of the standard accounts of perturbation theory. This is kind of like perturbation theory. Perturbation is a small change. So to perturb something is to make it adjust a little bit. And the idea is then that local and global minima can be reached when otherwise it might reach just a local minimum but not a global minimum in accounts of gradient descent or something like that. So accounts of the Monte Carlo Markov chains or the virial theorem or the hypothesis of small perturbations or perturbation theory, they're all just accounts of saying, well, it would go through zero, and then we've defined division by zero as undefined, and so that would be undefined behavior. But if we just have it be really small and just kind of jiggle its way past, then instead of having a paradox we'd have to solve, then it's just kind of restless, yet somehow again continuous. See, the idea then is like, and that's certainly a straight line. And it is an account of inductive accounts after the law of small numbers, a law of large numbers, criteria for convergence, and then for finding stability, local and global stability, the stable and the astable, vis-a-vis, usually enough, the adiabatic, not going back, it's not perturbative, the adiabatic and the non-adiabatic, or the diabatic itself. It's like it hops, skips, and jumps its way there. So when you look at the derivations of all the stack of dynamics and mechanics, thermodynamics and kinetics and all these kinds of accounts, it's smoothed over the jagged edges in a sense. And sometimes that's not correct. So the accounts then of this Poincaré's rough plane and Euclid's smooth plane and the Zolfrey metric for general relativity theory. And then for accounts of quantum mechanics, it's a continuum mechanics again, is for helping explain then for classical kinetics and kinematics why then rest exchange momentum and light speed rest frame theory end up helping look at it inwards from the other way with still the same set of concerns and considerations to get it to be sensible first, at least, that it's a theory like so, and then either show how it's the same account of fungibility or eventually the ultimate completions of the tractability. Hear about this emergence after convergence, because emergence is just the idea is like, well, convergence is to the limit. Well, emergence is like, is whatever it actually reaches in the infinite limit, not just the inductive limit, the infinite limit, and the continuum limit. Those usually being considered the same, but not really being so. Somehow it's related to the geometric series and the re-Vitali-ization of measure theory. That this double relativity theory is just another kind of example of what makes this sensible, fungible, and tractable, including all the entire standard linear curriculum's standard narrative of the thing in itself here, mathematical physics. Do they already have one of these? Yeah, there's a merely partial half account that's really great and very successful. It doesn't quite agree with itself yet. So, see, periodically driven nonlinear systems. So this is getting in account, usually the nonlinear systems, like, what are these nonlinear systems of interest here? It's like, they're ones that we can reduce to linear systems. Get back in the solvers. Vis-a-vis actual, otherwise we'd have to change the coordinate settings and like the entire approach to make for like Kodaira and Zariski and Lescope of the topological surgery that gets into account. So the integral analysis is like, you just basically have to change it all to integral analysis from differential analysis. And usually, unfortunately, one may aver, the case is by then it's like, well, by then I've already lost the connection to the integral analysis because my differential analysis is partial, and so my value criteria for these kinds of things is not fulfilled. I can't fulfill it. It's like, well, maybe you should have thought of that before you started chopping it off. You know, measure twice, cut once, and these kinds of things. Not to be brusque, not to be dismissive, yet to acknowledge that here it's then for the great account of a Duhamel principle of applying always the factors of integro differ and differ integro into these sorts of counts of otherwise the differential systems, and that it's an inertial system, as Einstein puts it, that all theories of relativity, the general sort, are. For example, in a discussion on page 96, the part says, consider small deviations of x, y, and z from their stationary values, writing epsilon n equals xn minus x naught, eta n equals yn minus y naught, and zeta n equals zn minus z naught, and taking note only of linear terms in epsilon and eta. Thus, by differentiating, one finds that then it results a sum of terms. And then the periodic components, this is coming out with it 2 times the amplitude. Usual accounts of the coefficients of amplitude that come out of analyzing systems of differential equations in terms of periodic functions, and what those are as placeholders. Besides that, algebraically, then arithmetically, they fall in line. The terms. Treat these other equations similarly and sort out the resulting expressions with the help of this other one to give the next step in these things. Eta n plus 1 and epsilon n plus 1. Given that there's a coefficient of this other small term, this is the deviations, perturbations or deviations, the virial, the life in it kind of, it's always moving, random motion and accounts thereof, and all these kinds of things. These coefficients form the A matrix, and T and delta are quickly evaluated. Chop. So this is just an example then that in all these sorts of accounts, this is very usual. Let's talk about orbits and stability. Here there's an account, instead of the geodesy, that's the orbifold. And that it's a perfectly suitable means to represent the behavior of the main beam of the intensity of light. It's just a different formalism that's less broken on the edges, although it's a little bit more complicated to figure out in the middle. From this equation before, we expect the approach to the stable orbit, just inside the triangle of stability. You see, this is kind of like triangle inequality is to set up the quadratic, and for matters of, it's a system of inequalities to say, well, it's not less than 1, it's not less than 1, it's not less than 1. We can add those up and say it's their sum. Here it's this triangle of stability is another account. It was like, well, in this region, according to all this error modeling of the bounds, as long as they're less than getting outside that region, they're inside the region. Triangle of stability, to be described by two independent modes of alternating sign. One should decay rapidly. This is the attenuation and dissipation here. There's a usual account of the sensible, fungible, and tractable here as tendencies and propensities of attenuation after dissipation and oscillation and restitution of the constitutive and the continuity of the things. One should decay rapidly as the power of the small terms, or the double power of the small terms, and the other slowly at a rate proportional to distance from the critical condition. This is confirmed by computation. And then he gives an account of checking the answer. Most always in accounts of differential analysis, it's like, okay, find a solution, prove its uniqueness, and find a solution. Now check it, and that it's not just absurd. For example, it would be in complex terms or something like that. The finding and the checking of the solutions is always present in an account of the grab bag toolkit of differential analysis. So this just gets into response and stability. This great book has a lot that goes on into systems of feedback and control and all these kinds of things that are necessary. Coefficients, descriptive terms, a proper calculation by Ornstein and Zernike, Ornstein and Zernike, give a very similar form to alpha, but with rather heavier scattering. The extra factor of about 4 probably means that the size of the fluctuating regions that contribute most to scattering is nearer lambda over 3 than lambda over 2. There is nothing unlikely about this. So here that's related to at least 3 things, one of which is halving and doubling spaces in the pi ratio space. Another is Ramsey theory, and then those both are about the quasi-invariant measure theory, helping explain why otherwise these two analysts arrived at different values. And then that gets into the laws of convergence, because there's these different laws of large numbers. The convergence, then emergence, where it's like, we added it up. It still doesn't match what we actually measured from an experiment that we expect to have the same model. And then we kind of multiplied it by 2 or added 2 pi or 1 over 2 pi somewhere, and now it works. These are accounts of continuum mechanics as naturally here. For the re-Vitali-ization of measure theory, where Vitali was a geometer who showed that he could split up the interval 0, 1, put it back together, and get 1, 0, 2. The collection of the individua of a continuum, since the act of individuation of elements of continuum, like making a particle in quantum mechanics, doubles its size in one dimension, and there accounts for higher dimensions. 1 through 3 usually. Lambda point anomalies in the thermal capacity. Pride of placements go to liquid helium-4, which below 2.17 kelvins is a superfluid, and which was the occasion of the name lambda point for this type of behavior, and the event has turned out to be quite different in its origin from the other examples named after it, and we shall discuss it no further. It's by no means the first lambda anomaly to be noted, but the first to be studied seriously, and it's not so long ago that it began to be recognized that the general properties they share are more significant than individual differences in detail. The overriding point in common is that there is no latent heat at a lambda transition. The entropy changes continuously, and there is no analog of two-phase coexistence, such as we find in first-order transitions. Of course, if the sample being studied is so non-uniform that the lambda point occurs at different temperatures in different parts, there will be a narrow temperature range in which some regions are above the lambda point and some below. But in a substantially perfect sample like liquid helium-4, if we ignore the very slight effect of gravity, The transition from the normal liquid to the superfluid below the lambda point affects the whole sample simultaneously. So this is non-local, is the usual idea. And it's for accounts of a continuous spot. It defines what a body is. So, and then anything that mentions anomaly after, instead of mentioning something like an effect, is it's physics. It's new physics, with regards to otherwise the usual account of the premier theory, and all of the descriptive detail. One may see an analogy between these structural, emphasis the authors, phase transitions and a stable symmetric transition, e.g. the Euler strut. The spontaneous shearing of the lattice with either sign of the shear angle is like the flopping of the strut to the left or right. And just as the restoring force for lateral displacements of the strut goes to zero at the critical load, so the shear modulus associated with a particular transition drops with temperature, more or less linearly, not exactly linearly, reaching zero close to T sub C. The same analogy is found in the ferromagnetic phase transition, where the inverse of the magnetic susceptibility, which is part of flux under flow, and so like infinitely fast flow of infinitely small amounts, usually, or half and half in a phase transition. About infinity divided by 2, or half infinity, the semi-infinite. The same analogy is found. Magnetic susceptibility falls to zero as the temperature is approached, at which no external help is required for alignment. Then he gets into Landau theory. We may now tackle the Landau theory, which assumes that the partially ordered state can be characterized by a single order parameter, eta, fluctuations being disregarded. So that's just kind of the account of, it's like, what's perturbation theory? Don't ask, because it's not, is the idea. If the sample could be kept disordered, free energy will surely be a smooth function of temperature. When ordering takes place, moreover, F is changed, and Landau assumes that the change is analytic in eta. Moreover, in such cases where eta and negative eta describe equivalent ordering patterns, the change will represent as a power series in eta squared rather than eta. So this gets on, because those terms would drop off. And then after first order, when they get truncated, it's like, well, they're left off. It's like, yeah, but out there, it's not left off. So this just gets into account then why Landau, from what Pipard describes here of Landau's, Landau's account of this, is present in every single derivation of physics usually found today, and anything that talks about dynamical systems or convergence. So this is a great little book, and helps a lot to kind of touch on, how to get there, and then what to watch out for. Or Landau's stipulation of analyticity. Introduction to the Physics of Gyrotrons by Gregory S. Nosinovich. So kind of like talking before about, that the gyroscopic effects have always been a part of physics, a special part of physics. And the whole idea of the centrality of the centripetal and centrifugal, the spinning the bucket, anything to do with projectiles that spin. So this introduction to the physics of gyrotrons has an account that the gyrotron would usually begin as account of like something that spins. So let's see what the authors might put up as what Einstein, as was mentioned earlier, would relate to Einstein's attack on Newton, or as with regards rather to his perceived defense of some of these zeroth laws about the difference between linear and kinetic and rotational and kinematic. This is when I found this book. I was like, oh, great, somebody's at least got a book about gyrotrons. Gregory S. Nosinovich, forward by Victor Granatstein and Richard Temkin. I paid $30 for this book. Or Introductions to the Physics of Gyrotrons. Johns Hopkins Studies in Applied Physics. Johns Hopkins University Press. Baltimore and London, 2004. Dedicates it to his teachers, Gapanov, Grikov, Patelin, and Yulpatov. Introduction to gyro devices. Electro and cyclotron frequency. Quantum interpretation of induced cyclotron radiation. So the idea that a linear accelerator and a ring cyclotron can put charged particles and uncharged particles together and just superimpose them and notice that there's a bump. This is it would be a definitive experiment establishing the reality of the difference among real space contraction of space-contraction-linear and space-contraction-rotational. That's a brief aside. Doppler effects, electron deceleration, gyrotron arrangement, electron optics, microwave structures, types of gyro devices, the theory of gyrotron oscillators and amplifiers, the gyromonotron, gyroklystrons. The klystron is a component is for the cyclotron, usually enough. But it's beam-wise, is my impression of it. Fluctuations, so fluctuations, another term for deviations in a sense. Intrinsic and extrinsic noise is fluctuations. The noise. Gyrotron oscillators, gyroklystrons, gyro-traveling wave tubes, other types of gyro devices. So on page 36 or so it was, or 96, let's see here. Types of gyrotron devices. Whereas chapter 13 is other types of gyro devices. Types of gyro devices, 36. Let's talk about Rayleigh genes. So the great account that goes in spectroscopy. Here, there's my bookmark is here on page 36 already. Types of gyro devices. The mechanism of the orbital bunching based on the relativistic dependence of electron-cyclotron frequency on its energy can be used for developing a large variety of devices. As was stated by A.V. Gapanov in 1966 at the Microwave Electronics Conference, Saratov, USSR. See also available references in Fliagen et al. 1977 and Andronov et al. 1978. A gyro counterpart can be found for any microwave tube driven by a linear electron beam. Key members of this large family are shown in figure 2.8. Here in the first column, one can see the gyromonotron, which we described already. Next is the gyroklystron, which is shown as simplest two-cavity configuration. Certainly the number of cavities can be larger. The two subsequent devices are those based on the electron interaction with traveling waves, the gyro-traveling wave tube and the gyro-backward wave oscillator. These devices are much simpler than their linear beam counterparts because gyro devices do not need any slow wave structure. Also, in the linear backward wave oscillator, the backward wave is a wave whose phase and group velocities have opposite signs. The phase velocity of the synchronous space harmonic is in Cherenkov synchronism with electrons, while the microwave energy propagates toward the cathode. On the contrary, the wave used in the gyro BWO, the backward wave oscillator, is simply the wave whose phase and group velocities have the same sign. These velocities obey 2.9, which would be it's an expression early in the text. So this wave propagates in a smooth wall waveguide in the direction opposite the beam. So kind of like the accounts of skin and core effect, and those being different accounts altogether of liquids and electrical current. The fluid, otherwise a fluid model. Here, this is giving this matters of flow and flux, which are real in these accounts of these systems of resonance, these resonant systems. It's going to be a while to get through this book. FM CAMs, KMM, bioethical prescriptions to create and choose and improve lives. Bioethical Prescriptions collects FM CAM's articles on bioethics, revised for publication in book form, which have appeared over the last 25 years and which have made her among the most widely respected philosophers working in the field. Bioethics is the idea of how to treat people when basically you have control over some aspect of their physiology or medical condition. It's an economical account. There's a moral importance argument. I'd have to read this a little bit more thoroughly to get an idea why it's any different than the usual idea of the Hippocratic Oath and primum non nocere. First, do no harm. Unstable agreement on a bottom line. The author suggested that the philosopher has a direct primary duty to express his own view of the best bottom line and reasons for it, as well as to mention seriously held opposing views. This implies that reasons of justice, consent, and fairness should be mentioned. In this case, however, it seems that we are dealing with some commissioners, emphasis to authors, who want only scientific interests to determine an outcome. Seeing this, the philosopher made it think that a morally acceptable course which attempts to reinforce the moral best of which these individuals are capable would be as follows. He should investigate thoroughly whether a system of compensation would indeed seriously hamper scientific progress. Well, that's basically giving an account of whether the state's healthy or not. Communicating in Mobile Systems, the Pi Calculus by Robin Milner. So the Pi Calculus is the process calculus. And so if lambda is the theory of types, then pi is the theory of communicating sequential processes. So in terms of communicating sequential processes or message passing, the Pi Calculus is a fantastic overall kind of setting for matters of formalizing and proving how protocols obey in matters of Pi calculus. So this is kind of an original kind of thing. It gives algebraic properties and equivalences. Gives cells and chains. He's got connections. A stack and counter. All the processes we have considered so far have a fixed structure. But many data structures change shape. So it talks about elementary accounts of state and scope. Here is the idea. Umberto Eco's A Theory of Semiotics intends to speak for itself. From the Advances in Semiotics Theory, General Editor Thomas A. Sebeok, S-E-B-E-O-K, 1979. The Emperor's New Mind. So here's Penrose's The Emperor's New Mind here. There is read Penrose's Road to Reality here. Ogilvy and Anderson's Excursions in Number Theory. I'll look at this a little bit more. Here after, like Kazaronov's inequality theory and what that's used to sandwich all kinds of things. Here it talks about phi, though. And it gives what it describes as a defining equation for phi with the x squared plus minus x plus minus 1 equals 0. And then that's related here to the molar gas constant, which is another root of that, and the Boltzmann constant, so that it's actually mathematical, not a physical constant, which otherwise it's let out to be. Because somewhere in the reductionisms is about Hooke's law and Clausius-Clapeyron and Arrhenius and the like. And then for Planck later, it's like so. The phi is another great constant. And then it's algebraic, if irrational. many great accounts of the recreational in mathematics. Piece of fiction, science, pulp. A Holy Bible. This one's the NKJV edition. I usually would read other ones, but it'll do. A Dictionary of Philosophy. Maybe that'd be something to discuss at further length. A.R. Lacey's A Dictionary of Philosophy. Let's see what he says about logos, I suppose. Mathematics, philosophy of L, M, J. It's alphabetically organized. Laws, logic, logical atomism, that the atoms in logic, terms, predicates, relations. Logos. The Greek concept has two basic and interconnected strands. One, the result of speaking, i.e. speech discourse theory, as again practice, sentences, story. Two, the result of picking out or counting, i.e. an account, formula, rationale, definition, proportion, and reason, both as reason as the power of reason. For example of English, of how the two strands tend to merge, see if recount, all told, see W.K.C. Guthrie, A History of Greek Philosophy. Then gives a lottery paradox, says. Yeah, the lottery paradox is just the fallacy of inductive empirical reasoning. Logic. So yeah, then this would have a lot going on in terms of a dictionary of philosophy. Well, gentle readers, that's the time for today. It's almost to the bottom of this book here, I suppose. Let's just kind of look to see what else is in it very briefly. Then we can get into quantum mechanics. The theory of relativity. So here's Muller's The Theory of Relativity. So I can read from this more about double relativity theory. Contributions to automorphic forms, geometry, and number theory. A volume in honor of Joseph Shalika, edited by Haruzo Hida, Dinakar Ramakrishnan, and Freydun Shahidi. Well, that's a bit dense. It has to do with many things. And then this last book in this box, Art of the Printed Book, 1455 to 1955. The Art of the Printed Book. Some of which have already been read here. Good day, gentle readers.